Hello geometry students. We're going to continue our study of circles in this video. We're going to look at a lot of information and see a lot of examples, so you may want to keep these notes handy when you go to do your worksheet. So let's start with this first situation where we have a line L that's tangent to a circle S at point T. Now, I think you've probably heard the word tangent line before. Well, yeah, we defined it earlier. So you'll recall that a tangent line is a line that touches a circle in exactly one point. So this line L touches the circle at point T, and notice we have a radius drawn to that point of tangency. So the first thing we're going to learn is the relationship between that radius drawn to the point of tangency and the tangent line. So you can see in the diagram we have a right angle symbol marked here. So what we can conclude is that if line L is tangent to circle S at point T, then ST, which is the radius drawn to the point of tangency, is perpendicular to line L. Okay, so let's apply that property to this example. So here we have a segment BC that's tangent to circle A. So CB is tangent to circle A. So notice we have this radius drawn to the point of tangency. So the first thing I want you to do is to put a right angle symbol right there, because we just learned that a radius drawn to a point of tangency will be perpendicular to the tangent line. So what that does is that creates a little right triangle, okay? So if it's a right triangle and we're looking for a missing side, then we can use the Pythagorean theorem. So Pythagorean theorem tells us that the square of the hypotenuse, which is AC, so what would be the measure of AC? This little piece is 2. So what about this piece? Well, you'll notice that this piece is a radius of a circle, and what makes a circle is the fact that all radii are the same. So that means that this radius is x, making the entire hypotenuse x plus 2. So using the Pythagorean theorem, we're going to say that x plus 2, the hypotenuse squared, is equal to the sum of the squares of the two legs. That would be x squared plus 4 squared. Okay, so first thing it looks like we need to do is we need to square this binomial. Remember, when you square a binomial, you're going to get 4 terms. The first term will be the first term squared, okay? Then you want to multiply the 2 terms together and double, so 2x doubled would be 4x, and then you square the last term, okay, and that's equal to x squared plus 4 squared is 16. Now, the nice thing about this equation, looks like we're going to have to solve a quadratic equation, except that we have an x squared term on both sides. So we can simplify this quite a bit by subtracting that x squared term from both sides, so we don't have to solve a quadratic equation. So that means that 4x, I'm going to go ahead and subtract 4 from both sides, is equal to 12, and so x is equal to 3. Okay, let's take a look at this next diagram. Here we have 2 segments that are tangent to circle D, and those segments are drawn from the same exterior point. So we have 2 segments from the same exterior point. I like to call this theorem the party hat theorem, because if you turn this picture sideways, it kind of looks like a face and a party hat on it. So what we get to conclude from this theorem is that those 2 segments that are drawn from those 2 tangent segments drawn from the same exterior point are actually going to be congruent. So BA is congruent to BC is our conclusion. Let's go ahead and mark that on the diagram. Okay, and then use that property in this example. Here we have segment GF and GH that are both tangent to circle J. So we have 2 segments drawn from the same point of, two tangent segments drawn from the same exterior point. So this theorem tells us that those 2 segments are congruent. So let's go ahead and put tick marks on there. And if the segments are congruent, that means their measures are equal. So 9x is equal to 5x plus 23. So I'm going to, let's see, subtract 5x from both sides. So I'd have 4x minus 5 equals 23. Then add 5 to both sides. And then divide both sides by 4. So we get x is equal to 7. Okay, the next several properties we're going to look at all will have to do with angles, and angles that are formed when we have either secant lines or tangents that are intersecting with a circle. So in this first diagram, notice we have sorry about that. In this first diagram, we have 2 secant lines that are intersecting in the interior of the circle. So our hypothesis is that AC, I guess I said segment AC, I could have also called this line AC. So either line AC or segment AC intersects either line BD or segment BD in the interior of the circle, but notice that they do not intersect at the center. The reason why this is important is because if this were the center, then angles 1 and 2 would be central angles, and we already know how to find their measures. So in this case, angles 1 and angle 2 are not central angles because this point is not the center. So let's first of all talk about how to find angle 1. Well, I know this may not show up on your sheet, but notice in this picture that angle 1, the intercepted arc, is red. And if you look at angle 1's vertical angle, its intersected arc is also red. And as it turns out, to find the measure of angle 1, we're going to use both the intercepted arc and the intercepted arc of its vertical angle. So the formula to find the measure of angle 1, we will find the measure of angle 1 by taking 1/2 the sum of those two intercepted arcs, okay? So the arc that angle 1 intercepts is arc AB, and the arc that its vertical angle, angle 2, intercepts is arc CD, all right? So to find the measure of angle 1, we will take half the sum of the measures of these two intercepted arcs, okay? So we can use that same idea then to find the measure of angle 2. So to find the measure of angle 2, we're going to take, again, 1/2 the sum of two arcs, and the two arcs would be the arc that angle 2 intercepts and the arc that its vertical angle intercepts. So that would be the 1/2 the measure of arc BC plus the measure of arc AD. Okay, so let's take a look at an example. Let's see if we can use this example to find x. So here we have two secants that are intersecting not at the center. So this 51-degree angle is the result of taking half the sum of its intercepted arc and its vertical angles intercepted arc. So let's just take those words and turn that into an equation. So that 51-degree angle is equal to 1/2 the sum of two intercepted arcs. Well, those two intercepted arcs would be the 74-degree angle. That would be the arc that the 51-degree angle intercepts, and then we add that to the arc that its vertical angle intercepts, so that's going to be x. Okay. Plus x. Okay, so now to solve this for x, let's simplify this equation a little bit. Let's get rid of this fraction by multiplying both sides by 2. So that means we would have 51 times 2 is 102, and that would get rid of the 1/2 on the right side, okay? And now if we just subtract 74 from both sides, we get our final answer, x is 28 degrees. Okay, so it looks like this picture is not drawn to scale, but you can check your work by adding 74 plus 28, taking half of that, and you're going to get a 51-degree angle. Okay, so that's what happens when two secants intersect in the interior of the circle. Now in this next example, or this next diagram, we have a tangent line and a secant ray. It could be a ray, or it could be a segment, or it could be a line. But what I want you to notice is their point of intersection. Their point of intersection is on the circle. So we have a secant and a tangent that intersect. Oh, I left out the word intersect. I'm sorry, but they intersect. Why don't we add that so you have that in your notes? So they intersect on a circle. All right, so let's talk about how we can find the measure of angle 1 and the measure of angle 2. We'll start with the measure of angle 1. And the measure of angle 1, this red 1 is going to use this red intercepted arc. And as it turns out, this will remind you of an inscribed angle. Remember, an inscribed angle was half the measure of an intersected arc, and the vertex of an inscribed angle is on the circle. Same thing here. Since this vertex is on the circle, to find the measure of angle 1, the measure of angle 1 is going to be 1/2 the measure of the intercepted arc, which would be arc AB. All right? And then to find the measure of angle 2, we will look at, here's angle 2. So let's look at the arc that it intercepts. It's a major arc. So the measure of angle 2 is going to be 1/2 the measure of the arc it intercepts, which is major arc ACB. Okay? All right, so let's use that for this example. We're asked to find the measure of angle K. So notice we have a tangent and a secant intersecting on the circle. So to find this arc, the measure of that, excuse me, to find the measure of that angle, we're going to use the intercepted arc. Let me grab a highlighter. This intercepted arc, which we're told is 186 degrees. Okay, so to find the measure of angle K, we're going to take 1/2 the intercepted arc, which is 1/2 of 186 degrees. So the measure of angle K is going to be, what is half of 186? Would be 93 degrees. All right, so now, what have we been looking at? First, we looked at angles whose vertices were in the interior of the circle, then angles whose vertices were on the circle. So now we're going to be looking at 3 scenarios. The first one has 2 secants, the second one has a secant and a tangent, and the third one is 2 tangents that are forming angles. But I want you to notice that in all 3 of those examples, where is the vertex of the angle? The vertex of the angle is outside the circle. So let's look at this first example. We have 2 secants that intersect outside of a circle. So to find the measure of that angle, that would be the measure of angle A, whose vertex is outside the circle. It's going to involve 2 intercepted arcs, this red intercepted arc and this blue intercepted arc. And to find the measure of that angle, what we're going to do is we're going to take 1/2 the difference of those 2 intercepted arcs. So that would be the measure of arc DE minus the measure of arc BC. I hope it's obvious to you that we want to always subtract the measure of the bigger arc from the smaller arc. Okay, so to find the measure of this angle formed by 2 secants whose vertex is outside the circle, we'll take 1/2 the difference of the 2 intercepted arcs. So let's take a look at this example. We're going to find x. Okay, so to find x, let's look at this 27-degree angle that's formed by 2 secants whose vertex is on the outside of the circle. That means that that 27-degree angle is going to be equal to 1/2 the difference of 2 intercepted arcs. Well, the 2 intercepted arcs would be this one, the 68-degree angle, and then the x-degree angle. So that would be 68 minus x. Okay, so let's solve this equation. So like a couple of examples ago, let's make the equation simpler by multiplying both sides by 2 and get rid of that fraction. So 27 times 2 is 54. So 54 equals 68 minus x. Then I'm going to subtract 68 from both sides. So I would get the opposite of x. Remember, when I subtract 68 from the right side, that leaves this negative sign in front of the x. So the opposite of x is equal to negative 14. And if the opposite of x equals negative 14, that means that x must be a 14-degree angle. Okay? So again, you can check that. If we take 68 minus 14 and take half of it, we should get 27 degrees. Okay? Now in this next example, we have, instead of 2 secants, this time we have a secant and a tangent, but notice where the vertex it is. The vertex of that angle is outside of the circle. So like the last example, to find the measure of angle A, it's going to be half the difference of 2 arcs. The two intercepted arcs are this arc, this arc DC and this arc BC. Okay, so to find the measure of angle A, we're going to take half the difference of the 2 intercepted arcs. And again, I hope it's obvious to you that you want to take the bigger arc minus the smaller arc. So that would be the measure of arc DC minus the measure of arc BC. Okay, so let's apply that to this example. We're being asked to find x. Here we have a secant and a tangent that intersect outside of a circle. So this 47-degree angle is going to be half the difference of, let me highlight, half the difference of this bigger arc minus this smaller intercepted arc. Okay, so let's write an equation for that 47-degree angle. It's going to be equal to 1/2 the difference of the bigger arc, this arc, which is x. So that's going to be x minus the measure of the blue arc, which is 102. Okay, So again, let's multiply both sides by 2 to get rid of that fraction. So 47 times 2 is what, 94? So 94 is equal to x minus 102. And then we'd add 102 both sides to both sides, and we would get that x is 196 degrees. Okay, in the next diagram, this time we have two tangents intersecting, but notice where where the vertex of that angle formed by those two tangents is. The vertex is outside the circle. So when we have two tangents that intersect outside the circle, it's like the last two examples. To find the measure of that angle A, we're going to take 1/2 the difference of the two intercepted arcs. Well, the two intercepted arcs would be this red major arc, so that's, let's call it arc BDC. So the measure of arc BDC minus the smaller blue arc, which would be arc BC. Okay, so notice that in this case, since it's two tangents intersecting, the entire circle gets used. So the measure of the bigger intercepted arc minus the measure of the smaller intercepted arc, and then you take half of that. Okay, so let's find out what x is here. So to find x, we're going to take half the difference of this bigger, oops, let me get a highlighter. Just 1 second, sorry. Let's take the measure of this bigger intercepted arc minus the measure of the smaller arc. Well, problem is we're not given the measure of this bigger arc, but since these are two tangents, we know that the red arc and the blue arc take up the whole circle. So to find the measure of this major red arc, we're just going to take 360 and subtract 110, and we'll get 250. So 250 degrees is the measure of that bigger arc. So to find x then, we will take 1/2 the difference of the two intercepted arcs, the bigger one minus the smaller one, so that would be 250 minus 110. So that's 1/2 of, let's see, 250 minus 140, and then 1/2 of 140 is 70 degrees. So x is equal to 70 degrees. Okay, so before we move on and talk about segments, I want to just summarize because we've talked about a lot of angles. So let's remember, it's not in this section of your notes, but remember we talked about central angles. If you have an angle whose vertex is at the center, not like this, but if you have an angle whose vertex is at the center, remember the measure of a central angle is the same as its intercepted arc. Okay, now for the rest of these, what you want to do is look at the vertex. If the vertex is in the interior, you're going to be taking the half of the sum of two measures. Okay, if you have an angle whose vertex is on the circle, so that could either be formed by a tangent and a secant like we have here, or an inscribed angle that we saw in the last lesson whose vertex was on the circle, then the angle would be formed by taking half of an intercepted arc. Okay, so if the vertex is in the interior, it's half of the sum of two arcs. If the vertex is on the circle, it's half of the intercepted arc. And then like in these three, if your vertex is on the exterior of the circle, you're going to be taking half the difference of the two intercepted arcs. So when you go to do your worksheet, what you'll want to do is look at the vertex of the angle and determine what arithmetic you do based on the vertex of the angle. Okay, so now we're going to switch gears and we're going to switch from talking about angles to the measures of segments. So in this picture, notice we have two chords, and we have two chords that intersect inside the circle. Okay, so what this theorem is going to tell us is when these two chords intersect, they chop each other into pieces. So this arc AC has been cut into segment AB and BC, and this arc DE has been cut into EB and BD. Okay, so what this theorem tells us is that when two chords intersect in a circle, then the product of the pieces of one chord, so product means multiplication. Let's look at this first chord, and the pieces are AB and BC. Then the product of the pieces of that first chord will be equal to the product of the pieces of the other chord. So that would be EB times BD. Okay, so this segment times this segment, that product will be equal to this segment times this segment. So let's use this theorem then to find x in this example. So you can see there's going to be a lot of algebra involved. First of all, let's look at this first chord. These two chords intersect inside the circle, so they chop each other into pieces, and the product of the pieces of one chord will be equal to the product of the pieces of the other chord. So let's look at chord JL that's been chopped into pieces x and x times 10. So their product would be x times x plus 10. I think I said times 10, I meant plus 10 a minute ago. So that product is going to be equal to the product of the pieces of the other chord. So those pieces will be x plus 7 and x plus 2. So that's x plus 7 times x plus 2. Okay, so we got a little bit of algebra to do, but the setup was pretty easy. The setup was based on this theorem that says if two chords intersect inside of a circle, then the product of the pieces of one chord will be equal to the product of the pieces of the other chord. So now let's go ahead and solve this equation. We're going to start by distributing and getting rid of these parentheses. So on the left side, we would have x squared plus 10x. On the right side, we're multiplying two binomials. So as you recall, that means there's going to be 4 multiplications. So we'll multiply the first terms and get x times x is x squared. Then we'll take the sum of the products of the outside terms and the product of the inside terms. The product of the outside terms is 2x. The product of the inside terms is 7x. So 2x and 7x is 9x. And then we'll multiply the last term. 7 times 2 is 14. So again, it looks like we're going to have a quadratic equation to solve, but you'll notice that both sides have an x squared. So we get to subtract x squared from both sides, and it turns out just to be a linear equation. So this will be pretty quick to solve. I'm just going to subtract a 9x from both sides. So our solution turns out to be x equals 14. Okay, now if you want to take the time and plug it back in, if you plug 14 everywhere you see an x's, then you can check and make sure that the two products are equal to each other. Okay, continuing our discussion of when segments, the measures of segments interacting with circles, let's look at this next diagram where we have two tangents that intersect outside the circle. So what we're going to look at then is we have this tangent AC and this tangent AE. Notice that AC has two parts. It has the part outside the circle and it has the part inside the circle, okay? And what we're going to do actually is look at the part outside the circle and multiply it by the measure of the entire secant. So in other words, we're going to take AB, which is the outside part, times the entire secant, and it turns out that that product will be equal to the other, if you look at the other secant, it's the measure of its outside part to the measure of its entire secant. So that would be AD times DE. Okay, so if you just remember this, you're going to take the outside part times the whole thing and set it equal to the other outside part times the whole secant. And of course, we're talking about the measures of these segments. So let's take a look at this example. We have two secants that, oh my goodness, I just realized I have a typo. Let's fix this. I said two tangents. Those aren't tangents. You probably thought I was crazy. Would you please change that? That should say two secants that intersect outside of a circle. That's what we have here. Two secants that intersect outside the circle. So the theorem tells us that if we look at the first secant and we take the product of the outside part times the whole thing. Now do not take 6 times 10. That's what you do when you have, that was our last theorem, when we had segments that intersect inside the circle. So it's not 6 times 10, it's 6 times the whole thing. So that's 6 times 16 is equal to, again, let's look at the other secant. Take the outside part, which is 4, and multiply it by the measure of the whole secant, which would be 4 plus x. Okay, again, don't take 4 times x. I know it's tempting to do that, but it's not 4 times x. It's 4 times the entire secant equals 6 times the other entire secant. So let's go ahead and solve that equation. We would get 96 equals 4, no, not 4. 4 times 4 is 16. Let me fix that. So 96 is equal to 16 plus 4x. So I'm going to subtract 16 from both sides, and I'll get 4x is equal to 80. Divide both sides by 4, and x is equal to 20. Okay? And then our last example, this time, again, we don't have two secants. This time we have a secant and a tangent. But notice where their point of intersection is. It's outside the circle. So the same idea is going to apply. Remember, this was the outside part times the whole thing equals outside part times the whole thing. We're going to do the same thing here, except in this case, the tangent, the outside part and the whole thing are the same segment. So JK is the outside part. JK is also the whole tangent. So we're going to take JK times JK. So that means we're squaring JK. And that product is going to be equal to the, let's look at the secant, break it into the outside part and the whole thing. So that would be equal to JL times JM. So JL times JM. Okay, so let's use that then to solve this last example. So again, we have a tangent and we have a secant. So the theorem says that if they intersect outside the circle, then if you take the tangent and square it, which is actually the outside part times the whole thing, so 8 times 8 is 8 squared, that's going to be equal to the other outside part times the whole thing. So the outside part is x, an expression for the whole secant, its measure would be x plus 12. Okay, so let's solve this equation. 64 equals, on the right, we're going to distribute and get rid of these parentheses. So we would have x squared plus 12x. Okay, so this is going to be a quadratic equation. I'm going to go ahead and subtract 64 from both sides, which means this side's going to be equal to 0. I'm going to turn the equation around also and just write it x squared plus 12x minus 64 equals 0. So let's solve this quadratic equation by factoring. So I'm going to find the two binomials I'd multiply together to get this trinomial. Well, if this term is x squared, each binomial has to start with an x. So I'm going to put an x and an x, okay? And then the next thing I look at is the sign of this third term. Remember, this third term is the product of these two terms. So if I multiply two things together and get a negative 64, that tells me that the signs have to be opposite. One of those numbers has to be positive, one has to be negative. That's the only way I can get a negative 64 for my product. So now, to get this middle term, I need to think of factors of 64, negative 64, one positive and one negative that add up to positive 12. So with a little trial and error, you should come up with positive 16 and negative 4. If I multiply positive 16 times negative 4, I'm going to get negative 64. If I add them, I'm going to get positive 12x. Okay, so then from there, we'll use the zero product property, set both of those factors equal to 0. That's the only way I can multiply the two factors together. This factor times this factor and get 0 is if one of those factors is equal to 0. So our two algebraic solutions then would be negative 16 and 4. But in context with this problem, what does x represent? X represents the measure of a segment. And in Euclidean geometry, we have the ruler postulate that tells us that the measure of every segment has to be a positive number. So even though negative 16 is a valid algebraic solution, it doesn't make sense in context with this problem. So we will just take our last example, x equals 4. Okay, so as I said at the beginning of the video, I would keep these notes handy as you go to do your worksheet. So you'll have them to refer back to. And if you have any questions, be sure and let me know.